All right, so here is our first official material for the grade 12 course. And so the very first topic we're talking about is vector concepts. So that's what we're going to talk about. This is what the first unit is going to be. And our goal is I can explain the difference between a vector and a scalar, which is very important, and I can describe the properties and notation associated with vectors. So we're going to talk about a whole bunch of stuff with regard to just the general notation and sort of getting everyone on the same base. Some of these slides are pre-filled, so you may want to pause the video and then fill in the material, or copy the material and then hit play and then listen to the commentary. So for people who have taken physics before, this is going to be old hat. For the people that haven't taken physics, this is more directed for you. So there are two concepts with the first particular component of this course, and that's vectors and scalars. So those are the two major concepts that you have to be able to differentiate between. So what is a vector? A vector will have a length, and now the grade 12 terminology that we move to is magnitude. So magnitude is a fancy word for length, and it has to have a direction. So a vector has both a length, or a magnitude, and direction. Now, length, most people are going to be thinking back to the physics, and length was the common one, but it can actually have any type of magnitude, and we're going to talk about some of those examples. So a vector has a length, or a magnitude and a direction. A scalar has a magnitude only, so there's no direction with a scalar. So we'll talk about some of the examples here, and some of them are already listed. So some of these are physics examples, but in the first column here we have our scalars. So let's look at the scalars first. So speed, when you're talking about speed, how fast are you going? You tell a person I was doing 80 kilometers an hour. You don't tell us forward or backward. We're kind of making assumptions, but speed does not have a direction. How far did you travel today? I went 100 kilometers. So distance is a scalar. Your mass, when I ask how heavy you are, you don't tell me I am 105 pounds upward or sideways. You just tell me I'm 105 pounds. So mass does not have a direction. Time does not have a direction, although we assume it to be forward always. If we look at our vector column then, velocity. Now velocity and speed are partners. Okay? Speed is a scalar, but velocity is a vector, and the difference is velocity has a direction. So if I asked you what's your velocity, you would tell me I was doing 100 or 80 kilometers an hour south or forward. Okay? Whereas speed, you're just giving me a magnitude. How fast are you going? So those are partnered up, and it's important to know the distance. And the way to remember, a car has a speedometer, which comes from speed. Most cars don't have a velocimeter, which tells you also magnitude and direction. Similarly, distance and displacement are paired up. Distance is just how far did you travel. Displacement is a measurement of how far are you from your starting point. So how far from starting point. So the example I have up here, take a quick look at what's up on this corner here. If I was going around a circle and I started here, if I started, let's start at home here, and I went around this large circle, and this circle, let's say, is 100 meters. So if I asked you how far did you travel, what distance did you travel, you would tell me 100 meters. If I asked you what's your displacement, how far are you from your starting point? Well, if I started at home and ended at home, then your displacement would be 0. So for everyone that sleeps in the same bed night after night, what is your daily displacement? Well, if you start in bed and end in bed, your displacement was 0. Was that how far you traveled? Definitely not. Okay? Now, weight and mass, these are often interchanged and done very poorly. Mass is the amount of material that makes up your body. Weight is the force acting on your body, so weight will actually have a direction. And finally, the extra, it doesn't match up with time, but acceleration is also a vector. And we're going to be talking about velocity, displacement, and acceleration and weight in this course. So for the people that haven't taken physics, it's going to take a little bit of practice, but there's some of the homework that will help straighten that out. All right, vector notation. Vector notation is starting right here, so I'll highlight where I'm starting. A vector is simply an arrow, and we're talking about geometric. And geometric, fancy word for picture. So if I was to draw a vector, it would start with a tail. So that's your starting point, and we call that the tail. So it's usually a dot, and where the vector ends, it has an arrowhead, and we call that the head. And the length of the vector is what we call the magnitude. So how long is that vector? That would be your magnitude. Our algebraic over here, algebraic, so this is how we represent it with words or letters. So the more common notation, and the one that I'm going to use mostly this year, is the name of the vector. So that's the name. And this symbol on top, the harpoon or the arrow, indicates that it's a vector. So when you're reading your textbook, or you see something in the notes, and you see a letter with a harpoon on top, you know that you're talking or referring to a vector. The other acceptable notation is boldface, but it's very, very hard for you to write in boldface. It's more of a textbook, so that textbooks it's easier to do, because making something bold rather than putting a harpoon on top is a lot easier. So those are your two acceptable formats for the algebra, and if we're drawing it geometrically, we're drawing an arrow. Okay, so a vector simply looks like that as a picture. Okay, so in reality, our vector, and I'm looking down in this corner down here, our vector will be given a length, so the 10 kilometers, and a direction, so east, 30 degrees rotated toward the north. Magnitude of the vector, or sorry, the difference here, I wanted to show magnitude versus the vector. Here we have what's called a vector, right here. Why is it a vector? Because vector u has a magnitude, 10 kilometers, and a direction, east, 30 degrees north. So those are the two components that make up a vector. Here, I only have 10 kilometers, which means it's only a distance. So this is a distance, which makes it a scalar. So there's no direction. It's only a distance. Now, how do I show that this is the magnitude of vector u? We use these horizontal bars. And people who remember absolute value, yes, they're the absolute value bars. So when you see these bars with some variable in there, so let's call it, we can go m vector, okay? The absolute value bars indicate magnitude only, which therefore we're just talking about a scalar. All right. If you're told an angle between a vector, the angle between two vectors, we call it theta, and this is the important part right here. The two vectors must be arranged tail to tail. It's the only way when you see a reference, if it says two vectors are 37 degrees to each other, the two tails have to be placed together in order to measure that angle. So that is key right there. So the angle between two vectors is measured when the vectors are arranged tail to tail. Scalar multiplication. So I'm going to put some numbers on these. So let's go with a 1. This looks like twice as big, and let's go with, keep this simple, 3. And put some letters on. So vector AB, CD, EF. So if my tail is indicated with an A, my head is with a B, this would be referred to as vector AB. This one's referred to as vector CD. So the name of my tail, name of my head, and then vector EF. Now I could have just called them, for argument's sake, I could have also just called this, I'm going to call this the U vector, I'm going to call this the V vector, and this one the W vector. If it's labeled with letters at the start and the end, the tail and the head, we typically use the AB notation, the CD notation, so on and so forth. So I want to talk about scalar multiplication for a second here. if I wanted to set some vectors equivalent to each other, so if I gave you this statement here, AB is equal to CD, we know it's not true because although the direction is the same, they're both pointing directly right, they're not the same magnitude. Well, we could fix that by saying if I double the length of AB, it would be equal to CD. All right, so we're playing with magnitude. So scalar multiplication, scalar just changes the length of a vector. Okay, so scalar multiplication only changes magnitude of vector. Very, very important, and plays a huge role for us a little bit later on. So only changes magnitude. I could have also wrote it, AB, vector AB, is equal to 1/2 the magnitude of CD. And again, this is only because they're in the same direction we can play this game. Similarly, 3 times AB is equal to EF. One of the things I'll comment at this point in time, this is going to be the hardest part for people that didn't take physics. People who did physics, I'm holding you to a higher standard, is to remember to put your vector notation in. Very, very important that you have your vector notation. So it's going to be the struggle for the first little bit, but once you get onto it, it goes pretty good. I could have also said AB equals 1/3 EF. So you can play a whole bunch of games. There's a whole bunch of equivalent vectors here. Similarly, if I set C and D together, CD equal to EF, and wanted to make that true, that one's a little bit trickier, but you're just playing with fractions. So CD, I could put 3/2. CD is equal to EF. So what I did was I divided by 2. So when I divide by 2, I put it back to a length of 1, and then multiply it by 3, which gives it that length of 3. Or some of you might have saw CD equals 2/3 EF. That's also correct. So there's a whole bunch of combinations. That's not all the combinations available to us. And the zero vector. Just want to talk about what does it look like graphically, because above you see vector A, B, C, D. Those are vectors that you can see. What about the zero vector? The zero vector is going to appear as a dot, which means the magnitude of the zero vector, and yes, it's a 0 with a vector symbol on top. Magnitude of the zero vector is 0. And it can point, so its direction, it points in all directions. Points in all directions. So it's a handy little vector because it can always be added or subtracted because it points in all directions, so it matches up with every vector that you're going to come across. Okay? So it's represented as a dot geometrically. All right. Next part here. Actually, I'm going to cut it off there and give you a break.